global debate on energy has become ever more relevant as of recent due to the rate at which climate change is occurring and recent economic indicators of peak war. As a result of climate change, global average temperatures have increased by a degree over the past century. It is therefore imperative that as a nation we investigate alternative forms of energy to reduce the concentration of greenhouse gases in our atmosphere. Wind power is a sustainable, cost-effective form of energy, which currently supplies 10% of the UK's energy demand. This year's L2 applications exercise seeks to investigate the power generation capability of micro wind turbines. We were tasked with designing, fabricating and testing a clockwise rotating horizontal axis wind turbine which should self-start at a wind speed of 10 meters per second, have a diameter of less than 500 millimeters and have a total mass which does not exceed 500 grams. There were some additional technical constraints on the wind turbine's performance, namely its maximum angular velocity should not exceed 3000 rpm and the maximum power coefficient should occur at a tip speed ratio of between 3 and 8.
The wind moves perpendicular to the plane of the horizontal axis wind turbine. Due to its rotation, the blades experience a component of wind velocity in their plane of rotation. From the root of the blades to the tip, this velocity increases, changing the direction of the relative wind vector. In order to maintain the ideal angle of attack, the blades have to be twisted accordingly. The lift and drag are proportional to the square of the absolute velocity, and so the aerodynamic forces increase along the span of the blades. These forces exert a torque that is transferred to the shaft and used to generate power. This is then expressed in terms of a non-dimensional power coefficient, defining the efficiency of the wind turbine in extracting kinetic energy from the air. Based on Betz's law, the maximum CP attainable is 0.593. However, for a small horizontal axis wind turbine, we would expect a value closer to a third. To begin with, we had to decide on a TSR, the ratio of the velocity at the blade tips to the oncoming wind speed. If the TSR is too low, the blades rotate too slowly, leaving some of the air to pass through undisturbed, and the wind turbine does not extract as much energy as it could. Spin too fast, and the wind turbine acts like a large disc. This results in huge drag forces. We opted to design our wind turbine with a TSR of 5. This decision was based on empirical data which suggested a typical value of approximately 5. The disadvantage of opting for such a high TSR is reduced rotor efficiency due to drag and tip losses. The objective of our aerofoil design selection and the blade planform design were to minimize these losses. We decided to choose an aerofoil which has a high lift-to-drag ratio, benign postal characteristics and sufficient structural cross-section. Using the Aerofoil Tools database, we narrowed down the selection to 3 aerofoils that matched our criterion at the operating Reynolds number of 60,000. We then used Xfoil to run our own simulations, testing the performance of each of these aerofoils. The results showed that the SG6043 was the best option. The planform design had several constraints. There should be sufficient lifting area such that the wind turbine self-starts at 10 meters per second. The blades should also be tapered along the span so that the circulation is constant. A short trapezoidal table was used as this gives 10% greater maximum lift-to-drag ratio than a standard rectangular profile. The final constraint was to ensure that the solidity did not exceed the empirically determined value of 7.5%. The optimal chord length and pitch angle were determined using Schmidt's theory. Q-blade was then used to determine the 3D performance characteristics of the wind turbine. Graphs of CP against TSR, drag polars, pressure distributions and glide ratios were plotted as a gauge of performance. The simulations predicted a maximum CP of approximately 0.32 at 2900 RPM for a TSR of 5.2. We were aware that these simulations had not taken into account surface roughness, bending, torsion or vibrations which could affect the performance of our wind turbine.
Once the aerodynamic considerations are taken into account, it is crucial to check if the design blade would survive during the test. So a structural analysis has to be done, accounting for stresses and deflections. There are many forces acting on a wind turbine. As engineers, it is important to judge which loads are considerable and which ones can be neglected. The critical stress of the ABS plastic used for the blades is around 21.6 megapascals, and the brake elongation is 3.18%. Aerodynamic and centrifugal forces were considered, and the rest were neglected, including weight and shear stress, as they were very low. These stresses had to be calculated independently and then added up to find the total stress. A MATLAB code was written to find the aerodynamic forces. We discretized the blade into 50 equally spaced sections, and we found the lift, drag, and moment acting at each section. Knowing the cross-sectional area of each section, the stress was calculated. The centrifugal force appears due to the rotation of the blade. To find this force, we approximated the blade to be a simple beam, so engineering's theory of bending was used. Then the total force was found by adding both forces. From this, the total stress was calculated and plotted against the distance from the root at a wind speed of 12 meters per second, which is the highest velocity at which the turbine would be tested. Therefore, the turbine would always be operating at or below these values. This plot shows that the highest stress would act at about 0.1 meters from the root, with a value of just below 1% of the critical stress. However, we know that the critical point of failure is near the root, hence a finite element analysis was done using QBlade, using values of stresses at 12 meters per second. This simulation proved that the highest stress was next to the root, at just above 1% of the critical stress. Therefore, it was important to design an optimum root shape. The chord length and twist at the root were estimated using the solidity equation, taking into account structural considerations.
The first thing we manufactured was the aluminum hub. We used a lathe and a process called turning to reduce the diameter of the initial cylinder. We then drilled the hole of 16mm through its center. The hexagonal shape and multiple holes of the hub were produced by milling and drilling with the help of CNC machine, which uses an automatic tool changer in order to perform the different processes. The thread hole was also drilled with the same machine. We then used a second lathe with a cutting tool in order to cut the final length of the hub. Finally, we performed a process called broaching to cut the keyway. The nose cone and the wind turbine blades were manufactured using a rapid prototyping machine and a process called fusion deposition modeling. The SD file from Korea is imported into software which mathematically slices the components, and then the material is deposited in layers until the 3D model is completed. In the workshop, we assembled the multiple parts by gluing them together, and afterwards we sanded the whole structure to remove remaining glue and improve the surface finish created by the prototyping machine.
When the wind turbine didn't work and couldn't generate enough lift to self-start, we immediately held a meeting. So we tried to find out why it didn't work and why it didn't produce enough lift. The answer was, of course, that we had designed our wind turbine for a TESR of 5. And that meant that we could save a lot on mass. But also it meant that we have designed our wind turbine for much higher wind speeds. Now that meant that it could not self-start at lower wind speeds. We changed the tip split ratio to 4, ran the simulation again, and we imported the geometry that was made by the MATLAB code into BTC Creo, and then tried to interpolate between this new geometry and the existing geometry, which meant that we either had to choose the leading edge or the trailing edge for this interpolation. We then decided that we want this interpolation done at the leading edge because that gives us more thickness, and more thickness means that it would be more tolerable for the 3D printing machine. So we connected the front surface of this new geometry, this new imported geometry, with the existing geometry, the front surface of this existing geometry that we already had, and then subtracted the geometry that we already had to get the modification that we needed, and 3D printed it.
After adding the leading edge extension, the turbine managed to self-start at a wind speed of 7 meters per second, as opposed to 14 meters per second prior to the extension. It then generated a maximum power of 19 watts at 12 meters per second. The corresponding maximum power coefficient was 0.09, and this was obtained at a tip speed ratio of 2.6.
Our choice of TSR was overly optimistic considering the size of our wind turbine. This skewed our planform design, resulting in a smaller surface area, so the lift produced was insufficient. Our design was essentially a scaled-down version of a larger wind turbine. The initial design was overbuilt structurally, as it did not fail even with the extra weights of the leading edge extension. To further optimize the merit function, we could reduce the size of the blade roots. This would also reduce the drag losses and the solidity. The modified design had a discontinuous leading edge. Given more workshop time, we could have blended the leading edge extension smoothly into the original blade planform.